Test, test, test. All right. All right, let's get started. All right, good morning, everyone. You've made it to this lecture. Good stuff. So organization, again, I've mentioned this the last time. The guest lecture next week will be held remote, the one on Tuesday, and on Friday we'll be here in person. Notes about the assignment. Assignment 3 will be released today. The plan is to release the solutions and the feedback to your solutions for assignment 1 today or tomorrow. That's the goal. And yeah, the deadline for the third assignment is a bit later than we initially announced, so it will be 13th December. And yeah, all the other questions, please, regarding the assignment on Piazza. All right, for today's lecture, we'll be talking now about implicit density models, namely generative adversarial neural networks. And we'll also be talking a tiny bit about diffusion models, which are an up-and-coming generative modeling method that's getting very popular at the moment. So again, this overview that we had the last time. So last time, basically, we talked all about Tuesday, about variational autoencoders on Tuesday, and also why generally we want to do generative modeling. So today, we're going to go to the other branch, to the implicit density branch, and talk about models from which you can sample from the probability distribution, but it cannot give you an estimate of what the probable or how likely a particular image is. So it looked as follows. Last time, we did all of the elbow amortization, reparametrization, all of the mathematics to get what is basically from something that's almost an autoencoder, which had this nice encoder-decoder structure, to arrive at a probabilistic explicit density generative model. So this is the image we had the last time. And today, we're going to basically put that aside, and now we'll be having something that almost looks like a decoder-encoder structure, and we'll be able to sample images from it. So it will be looking like described at the bottom. So we'll have real images from which we sample. That's just generation of a batch. And below that, we'll have some random noise as input. And then we'll have a network that generates new samples. So in this case, it will generate new images. And then the discriminator will simply be forced or be learned to be able to tell, is it a real image or a fake image? And by fake, I mean, or I will be using fake as a word to say it was generated. It's not from the data distribution, basically. And the discriminator will be trained in such a manner that it will learn how to tell between real and fake. And the generator, which will also be a neural network, will be trained in a manner that tries to fool the discriminator. But we'll go into detail in a bit. Before that, one more note about explicit versus implicit density. And I think this one nicely describes it. So if P star of X was the real distribution that generated the data, what we did on Tuesday, the explicit density models, we were trying to find a model P theta that assigns a high density to samples taken from the true distribution. So if X was taken from the true distribution, then P of theta of X should be high. That was essentially what we did. And today will be if samples are taken from the model P theta, they should behave similarly to real samples. So if we sample from our now implicit density model, then the probability of the real distribution should be high. So this is essentially the difference between explicit density and implicit density models. Yeah.
So in both cases, I'm assuming that our goal is to somehow model this probability density parameterized by theta.
Mm-hmm.
So in both cases, the outcome is similar in that we want P theta X to be similar to P star X.
Mm-hmm. Yeah. Note that in the bottom one, you can do the sampling, but you cannot actually get a value for this P theta of X. So that's what. So it looks a bit like you could, but that's the whole thing about implicit density, that you can do this like wave operation. You can sample images, but you cannot compute the probability values. Yeah?
Feels like you could stack these.
Sorry?
Feels like you could stack these.
You could stack these.
Using out the variational model, and then those inputs as the generator.
Yeah, I mean, in a way, a explicit density model like a variational autoencoder kind of does both, right? So it includes both things. So that's why explicit density is like a bit more difficult, because it can do both essentially. And in terms of variational and having an adversarial network, there exists some works that combine these things. But yeah. All right, so learning an implicit density function. So we've mentioned this, learning generally this data distribution function P theta of x is very hard, but hey, you've survived Tuesday. So instead, the approach we're going to take today is to directly evaluate if the generations are plausible. And if they're not plausible, let's get some gradients that's such that we can train the generator network. And then the question is, of course, what is a plausible generation? So we're still in the unsupervised regime. We don't have any labels. We simply have a training data set. And that's exactly what we're going to use via an adversarial network that tries to distinguish between the generated and the real data. And combined, these are called generative adversarial neural networks. Before we go into the detail of how it works, here are a bunch of applications and some generations. So for example, this was 2019, I believe, style GAN 2. And you can see these faces are pretty realistic looking already. This is an older paper which shows that you can use these GAN models not only for generating new images, but you can also manipulate existing images. For example, here you can put the texture of a horse on a zebra, and likewise you can put the texture of a zebra onto a horse. These models are so-called image-to-image models, because you're not going from Z space to image, but instead you're going from image to image, which means you can also do some style transfer, like try to have an image be in the style of a certain artist, or change a picture such that it looks like it's in a different season, for example. But there's more actual useful stuff that uses the same ideas. So if you can do that, you can also go from real images to semantic segmentation maps, for example, or vice versa. You can go from these to generate real-looking images that you can use as training data. If you, for example, don't have a training item where a car turns in the middle of a crossing, you can easily simulate that, for example, in this space, but perhaps you haven't seen it in real life, so you could generate this as an output. You can generate these sort of maps for satellite images. And there's a bunch more applications that actually are pretty useful. It goes further. You can also use it for generating fake data to train real fraud detection systems, or it's been used in some astrophysics. So there's really a couple of, or a lot of applications actually. All right, so let's go into the nitty-gritty details of how it works. It won't be as complicated as the VAE. It'll be pretty straightforward, I hope. And here's pretty much all that we'll be doing today. So on the left column, you'll see what happens if an image is sampled from the real data. So you sample one image from the data, you put it through this differentiable function D, which we'll just call discriminator, because now the discriminator for real image will try to return a value that's near 1 if it's from the real image. And then for the generated image, we'll be first sampling this noise, putting it through the generator network, and then we'll end up at some image. And at that point, we go through the same procedure, put it through the function D, except that now the discriminator tries to detect it being wrong, and the generator tries to fool this discriminator. So this GAN, so first again, The generative aspect is that you can sample novel input samples. You can create new images that have never existed. The adversarial part is that the generator is being trained to adversarially fool the discriminator, essentially. And the network aspect of the GAN abbreviation is, of course, that all of these are implemented as neural networks. Technically, they wouldn't have to be. You could literally define any other method that you could, with this kind of schematic, that you have one model which tries to fool the other. But of course, we want to be able to backprop through everything. And backprop is the way to deal with so much data. For those unfamiliar, adversarial simply means basically involving or characterized by opposition. So one has the other interests, basically, opposing interests. All right, so about this GAN training. So the basic principle is clear now, but why might it work, right? We start with neural networks which were initialized randomly. They're basically going to generate really, really, really bad generations at the beginning, and this discriminator won't have any idea what is a real image versus what is a fake one. And so the comparison we can make is, for example, of police and detecting fake money. So, for example, if the police wants to detect fake money, in this case, a fake image, basically, and they want to be as good as possible. And the counterfeiters want to make as realistic money as possible. And at the beginning, they're both very bad. Like, the money looks bad, and the police, okay, it's a baby, can't really do much. So now, it starts, well, you start training these, so the counterfeiter will become better, and then in order to still detect this one from the real one, the police will get better, and so on and so forth. And that's basically the intuition that we will have. You have this arms race, essentially, that one network needs to get better in order to fool the other one, which then leads the other model to get better. And this already, for some, might sound familiar. This is very much like in game theory, and arms race, of course, is also very popular topic of study for game theory from the Cold War, and relates to where you end up, relates to the Nash equilibrium from game theory. At that point, no one can improve their solution on its own. And it might not be the globally optimal solution, but that's how the Nash equilibrium is defined. Right? In terms of training, with training time, and of course it's not real time, it looks like this. You can already see there's some face-like shapes, features appearing. And in this case, it's a multi-scale GAN, so it tries to generate both pixels in this 4x4 space as well as in this, I think, 500 by 500 space in the bottom right. Yeah, and you can see that it's slowly starting to become more and more accurate and more realistic. And yeah. And in the end, you end up with pictures like these. Curiously, you might also notice that they're not particularly diverse bunch, and we'll talk about that one towards the end of the lecture. Yeah. Yeah. Yeah.
Yeah, I don't know if it's worth getting into, but then how are there multiple different scales?
This is just a method that we haven't talked about yet, and we'll not be talking about today. That basically, I mean, the main idea is pretty simple. Instead of just generating an image in one scale, you generate it at multiple scales. Idea, I think, mainly is that at the lower level scales, it's very easy to generate realistic looking images. I mean, you just need the skin colors essentially in the middle. But this already helps, and then the information sort of propagates through the different scales. I think you can also actually see that. Maybe, let's see. It doesn't work anymore. Yeah. Anyways, yeah, you can sort of see that it first starts generating something in the lower resolution, and then the details get like described in the other models, in the other resolutions. Yeah.
What's the relation between the police and the fake money in this example?
Right. So the police is essentially the discriminator, tries to tell between real and fake. And the generator, we're just looking at the output of the generator here. We're not looking at the output of the discriminator here. So discriminator is a police, generator is a counterfeiters, basically. Yes?
So I don't really understand for the discriminator. Okay.
Mm-hmm.
In the beginning, they're both randomly initialized
Mm-hmm.
networks, and the generator network can be trained from the discriminator's output.
Mm-hmm.
So that's real or fake, depending on what it outputs.
Mm-hmm.
But in the beginning, the discriminator, how can it evaluate that an image is real or it's fake? Do you need like a training set?
We'll go into how we train these in more detail now. Yeah, that's a good question. We haven't gotten to that part yet. So first we'll talk about the architectures, and then we'll talk about how to train them, what's their loss function, and then we'll talk about what's the problem with some of these loss functions, etc. All right. So this is another quite nice illustration. So you have the training set again at the top, and your images which are generated from some random noise, which is kind of looking like a VAE, but of course now we're simply using some random noise to generate images. So there's nothing probabilistic about it. And then you have this discriminator, which again you can see these trapezoidal shapes. So these are convolutional neural networks. Importantly, the GAN doesn't really have an encoder here. Instead, what it has is a discriminator, right? So it's still an encoder and a discriminator both take images in and output something. But in this case, it's simply trying to distinguish between real and fake. So the features that a discriminator learns are not necessarily as nice as, for example, the features that we talked about in lecture 6, where the higher level ones might be car tire or not, because maybe for detecting real versus fake, all you need is to find out if the image is particularly blurry or not, which in this case, that would be a very easy feature to detect. And that's why GANs typically do not end up with very blurry features if you train them correctly, versus VAEs tend to end up with these. As I said, we cannot compute the likelihood. We can only test new data points, only generate new data points. So the generator is any sort of neural network. It could also be an MLP. It could be a neural network which generates time series. It could be really anything. And we're still doing this sort of modeling where you start with a lower dimensional input Z and generate X, except we're not giving Z any particular constraints. We're simply sampling it from some distribution, and it doesn't even matter that much what kind of distribution it is. But since you're sampling it from, for example, a Gaussian distribution, 0, 1, without any correlations in between the different dimensions of Z, it means you can sample new samples really easily, because you just generate a new noise sample, and it's 100%, almost 100% likely that if you sample a new one, that this one hasn't been seen yet, and it goes through the network, and you get a completely new sample out. All right, yeah, different kinds of density functions. In effect, it looks like this. Usually you take, for example, a random noise vector, and you reshape it in some, for example, 4x4 grid, and then you do deconvolutions, these transposed convolutions, which end up gradually increasing the size of the spatial dimensions, and then you end up with some image. And with the transposed convolutions, you also have the bias inside these models that neighboring pixels are similar. And of course, that the operations are shared across the spatial dimensions, which is logical to have for images at least. The discriminator network, again, could be any sort of neural network, just depicting some MLP here, basically. And you either have the input from that was generated from the generator, or you input a real input, a real image in this case, and the generator simply needs to tell whether it's real or not. And in fact, how you usually do it, you mix them up in a batch. So you're not having one forward pass with only real and one forward path with only fake, but you mix them up, and then you get a mixed signal of like +1, -1, +1, -1, or zeros and ones actually. And the loss we'll be using is a binary cross-entropy loss. Because now we're simply trying to detect between one and another class. So the loss is binary cross-entropy loss. We want to output 1 for it being a data, for it being real, essentially. And we want to output 0 if it's fake. And we can write this out simply using the definition of the binary cross-entropy loss. You can ignore the WN. That's simply a weight function that we're not even using here. And yeah, you get this out because, well, you can see in the binary cross-entropy loss, you can see these two terms, but they are a linear combination of y times log xn and 1 minus y. And if y is either 0 or 1, one of these terms is going to cancel. And that's why you end up with this fairly easy structure here. So this is the loss. And then put together, you generate something, generates an image, and then you push it through the discriminator network again. And that's why the generator also looks pretty much like an inverse discriminator or like a decoder that we had in the VAE. In fact, the architectures are pretty similar. But yeah, you can also call these, you can call the discriminator, the decoder, etc. It doesn't really matter that much. And talking about words, of course, depending on what you're doing, network is a decoder or a generator. If it weren't for spatial dimensions, an MLP could also be a generator, an MLP could be a discriminator. It really depends on the context of how you call what. All right, so we had in the last picture, right, the starting point Z, in this case sampled from a Gaussian normal distribution 0, 1. So the starting point is this random noise. So what is true about this random noise? The noise acts as a regularizer for the generator. Noise models the random variations due to augmentations. Or 3, even if trained perfectly, not every Z that gets sampled will produce realistic images. Or 4, a fixed grid of, say, 1 million points would also work. They are very different points. Have a think about them. All right, let's, on the count of 3, let's see. 1, 2, 3. Okay, 2, 2, 2, 3, 1, 3, 2, 3, 3, 3, 3, 3. All right, so only few said 1, which is, 1 is sort of always true because you can literally call anything a regularizer. It doesn't really mean anything. It simply means it helps training. So 1 is always a safe choice. If whatever you have, you write a new loss function, whatever, you can always call it's regularizing. And don't do that because people will know that it doesn't mean anything. But people do use it sometimes. So 1 is fine. 2 is not true because you're not really using augmentations typically. Because you don't want a network that, for example, well, depends on the augmentations. Cropping is fine, but you typically do not want, for example, to output heavily color jittered outputs, for example, or you don't want to generate vertically flipped images, right? And noise isn't really meant for that. Then, even if trained perfectly, not every Z that gets sampled. It's sort of true, but it's trained in a manner, for number 3, it's trained in a manner that it should do, right? Because as long as you're sampling Z from your distribution, I mean, with a Gaussian distribution, it has infinite support, so you could end up with a point that is very, very far away, but it's very unlikely. And a fixed grid of 1 million points would also work. If your data set is small enough, for example, if your data set is just 5,000 points, then 1 million points is pretty close to being random at that point and should also work. I haven't tried it, but I believe it should work if your data set is small enough. Because even if your grid is a fixed looking thing, and your model needs to, for example, then map these to a dog and these to a cat, or it will do that by itself, I think that's pretty much fine because even the other starting point would be simply a Gaussian distribution or a uniform distribution, which is pretty much looking the same, and it would still have to do the same stuff. Yeah?
But wouldn't then every generated image be the same, or okay?
Yeah, that's a good point. So you would only have 1 million different kinds of images in this case, yeah.
Those are 1 million different...
Z's.
Z's.
Yeah.
Okay, I thought like a Z of a size 1 million.
Oh, right. No, Z, if that was fixed, that would be problematic, yeah.
Then it would be always the same output.
Yeah. You need to vary Z, yeah. The question is, yeah, I mean, for example, if Z is much smaller than the data set size, you'll have trouble, right? Because then you can only generate, let's say, 3 different kinds of classes, sort of, if you have 3 Zs, but your data set has 4 classes, then the discriminator will have a very easy time telling between what's real and fake. All right, so now let's look at how we train the generator. The thing also, I guess, similar to the point you just mentioned, is that we don't have the equivalent image in our batch, right? So it's not like we generate something that looks like a deer, and then we can compare it to an image of a deer. So we cannot quite do that. They're completely independent. They're simply generated from some random noise. So it's a bit strange that we would be able to give that simply to the discriminator and can train it. So the question is, how can we get meaningful gradients from that? The first version is the so-called minimax loss. So the simplest case is by simply giving the discriminator the negative discriminator loss. So basically, the loss of the generator is simply minus the loss of the discriminator, which makes it symmetric. And then the learning objective is this one. And the overall loss, and that's why it's called minimax, is that the discriminator tries to maximize its loss. That's the first part, maximize D of JD. And then the generator tries to minimize that thing. So you minimize that. And that's how you get a min-max loss. What you do, or where you end up with this min-max loss, is typically a saddle point, as the learning stops at some point. And at that point, for example, as depicted here, you have gradients being 0 in both directions. And this is just schematic. This stands for gradients overall for the discriminator or for the generator. And in this case, you're not getting any gradients anymore. So the generator will at first, the generator will first not receive any gradients anymore. And at that point, the discriminator will also not get any gradients anymore, which is, of course, not super great. It does allow for easy analysis, this min-max loss, but it will cause it to get stuck. Because the job of the discriminator is very easy at that point. So there's an adapted version of the min-max loss, which is a non-saturating loss. And the change is pretty easy. So you keep the discriminator loss as it is. And instead you use this generator loss. And now you cannot describe the equilibrium simply by a single loss anymore, as we did earlier with the minus point, and you don't end up at a saddle point. And yeah, the discriminator still, what it tries is to maximize the log likelihood of correctly discovering the real samples and the fake samples. And the generator maximizes the log likelihood of the discriminator being wrong. What you have here now is that the generator can learn even if the discriminator is very good on the real images. Because previously you had that the generator's loss is this mixture of how good the discriminator is on real images and how good it is on the fake images. And now the generator's loss only depends on the generator's outputs, which makes sense. Yeah.
One of the solutions before augmentation was supposed to create challenging images for a model to train on. So what is the difference between that and generative?
So augmentations are a way to train, and augmentations are a way to contain the same semantic content. So that's why they're, for example, used in supervised learning or self-supervised learning. what you generate with GANs can look like augmentations, and we'll go a bit into that point. But depending on the augmentation, so Z can model that, if that was the question, or
Yeah, I'm asking
the relation.
what is really the difference between those tactics?
Not sure if I get the question, though. So a generator is not a different augmentation, right? A generator has a whole different purpose that you actually can model and generate wholly new looking images. So it's not like these faces are just slightly blurrier or slightly brighter versions of existing faces, for example. These are literally new samples that don't exist in the real world, basically. And that's something augmentations cannot, I mean, you can see them as very, very, very high dimensional augmentations. But in this case, the only thing that's remaining is that it's both a face, but the whole identity is changed. So I wouldn't really call it an augmentation. But yeah. Question in the back? Sorry, sometimes I don't look in the back, so just.
You have the pulse here, which is a half for both the data and the generated things. So is that because you should do half of the generated image and half of the true images while training, or can you do any distribution?
Typically, you do half, but this half doesn't have much to do with that. So you could also be sampling 3 batches from the generator and 1 batch from the reals distribution and do this. This is now, I mean, you can leave out the half. You can simply multiply the learning rate by 2 and you end up with the same, or like divide the learning rate by 2 and you end up with the same. This is just so it looks nice because it's so you end up with 1 loss. That's sort of the average of 2, basically. Yeah, but yeah, keep in mind that you could, it doesn't, these batches are computed on average. So you could literally compute this loss with 10 times as many from this side, from the real one, and only 1, for example, from the fake distribution. Yes?
This last point, the generator learns even on the discriminator is too good on real images. I think a mixed question one is, what does discriminator is too good on real images mean?
It always gets it right, basically.
Okay, so even when the discriminator is perfect, the generator will still,
Yeah.
there are some gradients.
Yeah. Yeah, and we'll get an overview of how it actually looks like in 2 slides. There's just one third version of as well, which has been put forward, which is basically changing the generator loss once more and uses an inverse sigmoid, which has some advantages. That well, first of all, when the discriminator is optimal, the gradient for the generator matches that of maximum likelihood. So it's sort of a nice mathematics scheme. And it has some nice properties like shown in the following. So this plot shows you the gradient for the generator, and on the x-axis you have how good the discriminator is for generated content. So when the discriminator detects fake samples accurately, so that leads to a low value that comes out, right? Because the discriminator tries to give 1 to the real ones and low numbers for the fake ones. In this case, for example, the min-max or the maximum likelihood give you very low losses, low gradients. So that's not very useful. And so here, this heuristic loss is pretty good. So it yields good gradients when the discriminator is very good. That's basically how we motivated it as well. However, once the discriminator is not so good, or at the beginning when it's not so good, the ML cost, the maximum likelihood cost variant can generate pretty good gradients, and as compared to the green line, for example, which simply bottoms out and it doesn't give you much. All right, a different picture is the following. So now in the bottom plot, we show this Z space. In this case, it's one-dimensional. And we're trying to generate outputs in the X space, which is also one-dimensional. So we're simply plotting 2 distributions here. In this case, for example, the real distribution given by data is given in black, and that's not going to change. And the model distribution is green. So that's the thing that the generator will be adapting. Now we have the discriminator being simply a line. Well, at the beginning it's a bit squiggly, and after a while, and we'll be sort of showing the training iterations to the right, it will start learning. And it will try to output 1 where it thinks it's the real data, and it tries to output 0 where it thinks it's the fake data. And since these are also distributions, it sort of, for example, at the beginning learns this, and the second column learns this sort of discriminating function between the different points. Once the model distribution gets closer and closer, at the last point it basically models the whole real distribution. The discriminator cannot tell anymore between real and fake. So before they overlap, before the model distribution completely captures the data distributions, basically what the discriminator is trying to do is figure out where's the overlap the least, basically. At the last point, what does the optimal discriminator learn? It simply learns this ratio of overlaps, basically. So the probability that you have for a given data point, for the real one, needs to be, well, this is literally the formula for the overlap, right? So you get the probabilities for both, and you simply put them in this equation. But the question is, okay, I just put this here, and this sort of heuristically motivated from these pictures. But let's take a look at why this is actually the case. And it's actually not that difficult. So here we have written the loss for all the data samples X and all the generated data samples Z. And that's why we do the integration here. Now in the second row, we change the integral from going over Z to over X, which you can do by just giving it, we are simply reweighting these probabilities in the integral. And now this doesn't look as easy yet, and we wouldn't know, okay, where do we end up with? But if we actually differentiate this by D, by the discriminator, we can use a formula from mathematics again, that A log X plus B log 1 minus X has a maximum at A divided by A plus B. And this is exactly the type of formula that we're having here. So we have A, which is P data, log D, that's the X that we have, and yeah, so you plug these in, and then you get the optimal discriminator as this. And at optimality, you have that the generated distribution approximates or goes close to the real distribution. And so you plug these in now, right? And you simply get that the optimal discriminator ends up at 1/2, which is what you ended up on the previous slide here. So it ends up simply at 1/2 because it cannot tell anymore. And the loss at that point, if you plug it back into the loss formula that you get, is minus 2 log 2. All right, and with that, let's take a quick break until yeah, we can do until 10, I think. And then, yeah, but let's start exactly at 10, though. All right, let's continue. All right, we're going to continue now. Thanks. All right, so there's a deep connection between GANs and the Jensen-Shannon divergence. The Jensen-Shannon divergence, again, sounds fancy, is defined here in gray. So what it is simply another metric that compares two distributions. And in this case, it simply compares them by taking 2 times the weighted average of the Kalberg-Leiber divergence. And it's defined here in gray. And you just plug this in now, and you write this out for the optimal discriminator, and you get this term out. And now what you can see is that you get these 2 integrals back, which is exactly the definition of the loss that we had in the previous slide. So we can rearrange this, and this is, of course, like a very educated guess of simply writing out the JS divergence like that. But now we can write out that the loss that we're having is actually 2 times the Jensen-Shannon divergence between the 2 probability distributions, which is quite nice. And we found out that, of course, for the optimal case, this loss was minus 2 log 2. And so if the loss is like that, that means the Jensen-Shannon divergence is minimized. So again, we are getting this other point of view here with these divergence measures, that what we're optimizing is actually the JS divergence between these probability distributions. So this gives you like a bit of an insight about that. The question is, of course, why is it the JS divergence? It could be any kind of other distribution, any kind of other divergence measure. There's the KL divergence, of course, that we've had, but there's a bunch more. And we can compare these as the main ones that we've been talking about. And the main thing to look at, and this sort of gives you the broad overview of what all the kinds of comparisons that you can take when you have 2 probability distributions, and you can compare them against the medium, the average of 2 distributions, which is here the M, and you can show how the distributions, how the divergences are looking. So these are the ones that are being plotted everywhere apart from the top left. And importantly, the Jensen-Shannon divergence, of course, is symmetric. That's the key point here. And rehashing this point about that it matters which divergence measure we take, we have the same plot from the last time, that depending on what you do, you will either capture something that's in between 2 modes of the data, which is, of course, not really, you won't get any samples which are realistic, or only rarely, or you capture one mode, that would be, for example, with the reverse KL. Except in our case, it's the other way around, so the KL will give you the mode capturing. So depending on how you write, you will have this sort of risk aversion behavior or this mode capturing behavior. And for the backward KL, this is also called zero forcing, which makes the model conservative. And it will try to avoid putting probability mass where there's none. So it will avoid these 0 areas. Whereas for the other way around, it's completely fine. All right, so yeah, this is sort of the general observations that we have about GANs, and that's pretty much all there was to the information theory part. For the training procedure, we'll be simply using the same that we've always done, SGD or ADAM, perhaps some weight decay. And we talked about having to use 2 mini batches simultaneously. Typically, these simply get mixed. And there's the option to run multiple steps of one network for every other step, for every step of the other one. There's a bunch of heuristics here. There's no consensus on which one works better. In the end, you will have to try, and there's some overview papers which tell you which one works better, but there's no rule here at all, pretty much. Right. Last time we didn't have one. This time we'll have one. How research gets done. Now we're at part 8. At the top is Katalin Kariko, who's a Hungarian-American biochemist who specializes in RNA-mediated mechanisms and who has been super responsible for the mRNA vaccine of BioNTech. All right, so at the top we have the previous parts where the last one was, okay, when not to give up and how to weigh like the potential impact versus the work that you need to put in. And so now we've arrived at the point where you didn't give up and you're on to something that sounds interesting or looks interesting. So now how can you show that indeed what you're doing is meaningful, is better, or how do you understand that? How do you understand what's happening? And the one important answer to this in deep learning or in machine learning is typically what is called ablations. The key idea here is that you only vary one thing at a time. And it's the same principle. So this is for both for writing papers, for showing it to other people, as well as when you design it yourself, when you're trying to investigate what's happening. Only vary one thing at a time, because otherwise you won't know if it was A or B that helped. So if you change the learning rate, but you also change the data set, you won't know whether that if your model suddenly starts working, you won't know whether it was your learning rate that was better or it was the data set. Some examples of how such ablations look like, for example, in papers, is typically like this. For example, here, the left one, you have these crosses versus check marks. It simply means, did you use it or did you not use it? Or in the other one, the table to the right, for example, each ablation has a subheading. In this case, you're ablating the backbone architecture, and you can already sort of make sense of it. So you have resonant 50 versus resonant 101, resonant 50 versus resonant next, and so on. You pretty much immediately get what's happening, and you can see the numbers were bolded for the bottom. So these are the best numbers. So you know, okay, this backbone apparently gives the best numbers. Similar, you compare like multinomial versus independent masks, which were softmax versus sigmoid, and then you see, okay, apparently sigmoid gives the best performance, and then below that you can see the delta. So immediately it's clear that only one thing is being changed, and you figure out what's the important part here. So apparently sigmoid was an important part for that paper, or led to the biggest improvement, for example. Sometimes it's also important to show really simple and easy to understand cases. And this could be toy examples. So sometimes you need to design a data set or a task by yourself just to prove the point that what you're doing is actually doing what you think it's doing. And this is very much often the case for reinforcement learning, for example. And crucially, and we'll basically go into paper writing the next time, but importantly, you only need to focus on one idea per paper. And that's an important thing. You don't get distracted by all the other things. If you end up doing something that's tangentially related, but only, for example, gives you 0.1% benefit, then probably it's not relevant for the paper and you might as well leave it out. Typically, things like that are ensembling, because ensembling of models you can always do, and it pretty much always gives you better performance, and that's great for calculus competitions, but you almost no paper does it, unless the paper is about ensembling, for example. All right. Is it stuck? It's stuck. All right. Back to nightmarish pictures. So challenges of training GANs. So we've already mentioned that the loss is a bit, there's 3 versions of the loss, and the original one, the simple idea of min-max, doesn't work actually that well. And so we had 2 other versions, and even then there's still a bunch of challenges. And everyone who has trained GANs will have generated pictures like these at the top. I've also had these. This is what you get when your GANs don't train, basically. And that's kind of nice. At least you can investigate it and see how well they're doing apart from the loss function, right? All right. So vanishing gradients, as so often, is a big problem here. So on the right figure, what you have is a picture of having a GAN model as it is for either 1, 10, or 25 epochs. And now you keep the generator fixed. And you only train the discriminator for a few iterations, so from 0 until 4,000 iterations. And what you look at, and that's the y-axis, is the loss that you would get to the generator. So you're keeping the generator fixed, but you're simply looking at the loss that the generator would get for this given discriminator. And what you can see here is that the loss is given in the absolute magnitude. So you have a log scale on the y-axis. And you can see that when does it write? Do I have it here somewhere? No, sorry. Well, you can see, for example, the blue line goes from 10 to the 0 all the way to 10 to the minus 3, so it crosses 3 orders of magnitude. The red one even crosses 5 orders of magnitude. So that's the discriminator can really learn to distinguish this real versus fake extremely quickly. And at that point, your gradients are only 10 to the minus 6 anymore. So at that point, you're not getting any gradients anymore if the discriminator is really good. So the gradients will go to 0. If the discriminator is quite bad, the generator won't get any good gradients as well. So you won't be able to get good training here. So especially early in the training where everything is bad, the discriminator will have a slightly easier time because it can still latch on to like these weird patches at the edges or to blurry parts, etc. So some solutions are, for example, that you give the generator more iterations, or another one is that you add an encoder that encodes a real image and then discriminates on this encoding and the image, and that's something we'll talk about later. Yeah.
I'm just confused about what this graph shows. So, is it showing the norms of the gradients of the discriminator, or the generator? Because it seems like the title says of the generator, but the caption says of the discriminator. If I'm reading it properly.
Gradient of the generator, I think. So you keep the generator fixed. So you just compute the gradients, but you don't apply them, and that's what's being plotted. So, yeah, if it was the first step, you could still do the same, and then you would be in normal backprop regime. But here you're just getting the gradients, saving them, and plotting them, basically.
And the number of epochs refers to the number of epochs we've already trained the generator.
Yeah, exactly. So it's that's why I sort of tried to explain this plot step by step. It's not a plot you would usually do where you have different kind of models as starting points and then you do these iterations. But it sort of shows you this nicely, basically. Yeah. Any other questions? All right. So the other challenge is the low-dimensional supports. So we've talked about this earlier, right? That low-dimensional manifolds, they ideally capture, for example, a theme or an object. And once you have that, all the pixels can be generated from that quite easily. So that's why this low-dimensional Z space or embedding space makes sense. However, if this low-dimensional space is these manifolds, which last time we represented either as surfaces or lines. Let's say these are lines, for example, lines in a 3-dimensional space. They pretty much don't overlap at all. So it's very easy for a discriminator to simply put a line through these. So yeah, especially during training, the generated manifold is not perfect completely not perfect. So it's extremely easy for these models to discriminate between these because the Jensen-Shannon divergence, well, it's also problematic because the JS divergence actually gives you extremely low value if they don't even have an overlap. So you kind of have this chicken and egg problem that the loss will start being meaningful once your generations are good. Here there's one solution which is called WGAN, which basically uses a different metric to compare real versus false. And this one of the GAN variants that we'll quickly mention later. And yeah, so even if you had like 2D surfaces, such as here, you can see that the overlap overall, the data which sort of would contain the same topics, and these are just schematics, of course, would be fairly low just within this one line where the two surfaces intersect. Right. Another problem is batch norm, because batch norm always causes trouble. So batch norm here is because you're mixing, for example, batches of real images and batches with not real images. So, and you compute the batch statistics from that. So that usually leads to very smooth but awkward looking failure cases. So what you can do instead is you can keep a reference mini batch. So you train with 2 mini batches, and you simply have a fixed reference batch that you use to compute all these batch norm statistics, like the mean and the standard deviation. And then you use the other mini batch for training. So that's pretty easy. However, at some point, this lack of variation with regards to this reference patch will give you a bit of a trouble. Because one of the main benefits of batch norm was that it sort of gives you this slight variability and this regularization effect, basically. So you can sort of try to fix this one in turn by simply concatenating the reference batch to the existing batch. And at that point, you have, of course, the trouble that the GPU memory you could run out. So in the end, I think the going advice is to simply not use batch norm. And this is what all the major large and good GAN-based models are doing. For example, they use instance norm, which is completely, it does not have any batch dependency at all. In fact, actually what they use is adaptive instance norm, which is, you can see the instance norm formula there, x minus mu divided by sigma plus mu, and simply normalized one more time. All right, so the next difficulty is convergence. Yeah, so finding a saddle point is pretty difficult, and these models can train for weeks, and mode collapse is one of the most severe forms of non-convergence. So mode collapse, I've mentioned it briefly in the topic of the KL divergence. For example, if you have this simple target distribution of these 8 Gaussians, and you train a generator model, it sometimes will simply fit towards one of these modes, and it will have a very difficult time fitting all the different modes of input data. And similarly for image-based models, you can see, for example, all these images of flowers within a single flower category, for example, they pretty much look exactly the same. So there's no variation captured at all. It's simply capturing one of the modes. Yeah, so the generator will place all the mass in there, because if the discriminator is simply trying to discriminate between is it looking real or not, well, the generator has the easiest time just generating one sample which looks very, very real and not caring about diversity at all, which is, of course, exactly not really what you want. And so a solution will be to talk about adding some diversity as a regularization loss, basically. And in fact, this regularization is quite real as a problem. So, for example, one of the things that GANs can cause is this mode collapse towards, of course, white-looking features. For example, in the Snapchat face lenses, where they have used GANs, and if you augment your face, and there's some filters apparently, you end up looking whiter, for example. And so this can be, for example, explained by something like mode collapse. I mentioned the potential solution. It's fairly simple. You simply compare a single sample to the other samples in the batch, and you check whether you can discriminate between these two. You look at, okay, what's the entropy within the samples, and you can simply add this as another loss. And then you need to, of course, balance it, because if you simply enforce a huge amount of entropy within the mini batch, then this will give you very different samples, but they might not be leading to realistic images anymore. So generally, you need to balance between these 2 points, basically. This overgeneralization, where you generate images which go beyond the training data set. And if they go beyond, this simply means they're not looking realistic usually. It's not like if you train on cats and dogs, you will be able to generate images of airplanes. Instead, you'll be generating some sort of noisy structures. And mode dropping, which is if you train on cats and dogs, you'll be only generating images of dogs, essentially. Yes?
model here covers a Gaussian area, right?
In the latent space, the models cover Gaussian areas, yeah.
Yes. So would that be a drawback? Would a more flexible distribution work better in this case?
I believe the distribution you have in the latent space doesn't matter too much. I mean, at least empirically it doesn't matter, because essentially, and that's sort of what you do, is you take this Gaussian distribution and you mold it all the way until it becomes super nonlinear anyways. So even if you made the initial distribution less linear and made it star-shaped or whatever, it wouldn't help that much. Unless you have, of course, knowledge. Unless you know there's 8 classes, then you can probably model it as a mixture of 8 Gaussians, for example. That would make sense, and that would probably the model would be able to figure it out, for example.
So then in that case, this sort of diagram is oversimplification because...
These are always oversimplifications, yeah. Because, yeah, I mean, the round area is not, it's not meant to like illustrate the Gaussian that we talked about in the latent space, for example.
So would more complex models be able to fit to... Yeah, I think we can go on with the lecture.
Okay, yeah, so generally, like if you imagine like the generator model just being one layer, the outputs will still be looking pretty Gaussian, right? So once you start having 10 layers, you can start modeling distributions which look very, very different. Yes, question?
Wouldn't the discriminator, like in this multi-dropping scenario, wouldn't the discriminator at some point realize, well, most of the dog images I get are fake, even if they look realistic, and penalize that? Or is it just...
So if the...
Like saying the generator figured out how to generate realistic dog images.
Yeah.
Wouldn't the discriminator not at some point realize that dog images are more likely to be fake and penalize that?
Yeah. Then you would have some sort of cat and mouse game where it simply jumps, like it could...
So it makes realistic cats.
Yeah, and you do see this sort of behavior in GANs, yeah.
Okay. If I may add a second question, how do you penalize similar images? Like, how do you compare? Like, you look at the mini bench and say, well, it's only images of dogs. I want to penalize that. That's the idea, right? How?
Yeah, there's a bunch of ways. You can either, let's say the simplest thing is, for example, you force the embeddings to be different at some deeper layer. You can also try to have a classifier which classifies, is this sample different from the others?
So that's like the domain knowledge and finding out what works.
Yeah, pretty much. Yes?
Sorry, you kind of confused me now. The similarity is not, is it meant because you phrase it as if it's the same class? I understood it that within the same class it's like one type of dog that looks very similar to, and not like a different augmentation of the same dog.
Right. So it really depends whether we're talking about the conditional setting where you have labels or not. So if you are in the conditional setting and you know you're generating dogs, but they all look the same, then this is the case that we're talking about that. In the case of unconditional generation, pretty much what we're mainly talking about, then it will be about, okay, it's only creating dogs, but not cats. Yeah?
Let's assume that our data set has classes, say dogs and cats, but they're unlabeled. So our GAN would learn to generate images of cats or dogs or both, depending on training, I guess. So say that the data set itself is biased, say 90% dogs, 10% cats. Then this comparison measure would lead to the overgeneration of cats.
It depends how you implement it. I mean, I haven't given any formula for the comparison measure, so it really depends. But if you have a data set like that, very likely it will only generate the majority class, unless you're careful about that. All right. Another challenge is how to evaluate these generative models. So looking at images is nice, but we also need to quantitatively evaluate them. So there's something called the Fréchet inception distance, and it's pretty easy. You push basically the real and the generated images at the same size through a pre-trained inception network. So that's a neural network that we had talked about. It's simply pre-trained, and then you use the dense features, and then you compare these dense features. You actually fit a Gaussian model to these features, but it doesn't really matter. You simply take the difference between the data set-wise features, and this will sort of tell you how good a set of generated images matches another set of images. So if you're completely mode dropping, the FID will be low because the distance to all these stock images will now suddenly be pretty high. And it will also have deep features. So if these things don't look at all like the real classes, the distance will also be high. Yeah, so it's of course, and I think we discussed this point in the break as well, like what about medical tasks, right? Like, can you even trust these methods? It's pretty tricky. Question?
Why specifically an inception network?
Yeah, that's a good point. It has been sort of the default, and it is pretty good at yielding features at giving like features which correspond well to how humans perceive something as good. So you can, for example, you can compute FID of various networks against whether humans think this image looks realistic or not, and they sort of found that this network gives you a pretty good measure. Yeah.
Can it be related to having like different filter sizes?
It is somewhat, yeah, it is. I mean, because whether it's inception or VGG or whatever, the only difference is the architecture. So it is related to the architecture, but yeah, that's just a method that's being used, yeah. All right, so of course we can generate anything beyond images as well. The only difference is, difficult thing is if you have text, you need to do something else, right? Because suddenly text are discrete chunks, so you cannot model text as continuous variables where you can simply push gradients through, which is what we're doing for RGB outputs. We're simply pretending like they're continuous. And similarly for other outputs like graphs. All right, so the challenges are, of course, the trade-offs between GANs and other generative models. We had the VAEs, which might be, which are usually a bit better at disentangling, and we'll be talking about diffusion models in a second. The modeling aspects, the convergence aspects, the difficulty of evaluating them, and of course the slight arbitrariness of how we evaluate them quantitatively with the fit measure and the inception networks. The scaling is always an open question, and whether there's any relationship to adversarial examples. All right. Then GANs also sometimes explode. That's how it looks like if you're training something and suddenly all your measures, for example, the fit score, it usually goes down, right? It's a distance to the real data set. Suddenly it goes up. And this is quite common that this happens. All right, so let's talk about some GAN models and applications. So basically, you went from the top to the bottom in the matter of 4 years or something of research. So the initial neural networks, they simply looked like the following. So it's a simple deconvolutional neural network, pretty much like the one that we talked about in semantic segmentation tasks. And back then, the examples, you would have to train them on a data set which doesn't have that much variation because otherwise it wouldn't even train. So typically, they trained on face data sets or bedroom data sets, something like that. But even back then, you could do some interesting things like sort of similar to word2vec, where you have the encoding of a man with glasses, and you subtract the feature vector of an image that generates a man. You add woman, and then sort of what you end up with is basically a woman with glasses. But of course, I mean, this doesn't always work perfectly. But even back then, you can sort of get these interesting features. And we actually talked about this briefly in the break, but you can use these sort of things also to train semantic segmentation models, right? Like if you know, for example, the first picture is man with glasses, then in all of these 9 other pictures, you could now segment if the identity, for example, of that woman was kept, it isn't really here, not that well at least, then you could learn how to do semantic segmentation. And some people have used GANs for training semantic segmentation models. GANs are also great at creating fake data that can be used for training. For example, you can generate all these kinds of new augmentations. So in the bottom left, you see the original. So you have the dog and the car. And then you can generate all kinds of augmentations from a really good GAN model. So the really good model is a style GAN 2. Similarly, for these, you can create, for example, different angles of looking at a cat, or different angles for the car, and even different colors and like that. And with that, you can, for example, augment your training data set. Right. I briefly mentioned this at the beginning. There's another way to train a GAN, which is called Wasserstein-GAN. It simply uses a different metric, and the main thing is that you can sort of get gradients even if you have no overlap in these distributions at the beginning. So in this case, you can see these two probability distributions. This, again, for real and fake, we're talking about simply a 1D thing. And even if the discriminator is having a really easy time at discriminating between these two, you're still getting gradients, basically. So that's a simple hack that has been done. However, and that's why I'm not stressing too much on the details here, what they found in a paper already in 2008 is that all the GANs up until then yielded pretty much similar quality, and they all needed extreme tuning of hyperparameters, which is, of course, not something that you wanted to do. So all of these variants more or less led to the same results. So only the stuff that I'm going to talk about now is the stuff that has really progressed and kept on having good performance. So one thing is the big BiGAN that I've mentioned the last time. So I've mentioned that compared to an autoencoder or compared to a VAE, you have this additional encoder part. And we had the generated images. And so the key part about big BiGAN is that the discriminator works on images and Z, so this, let's say, 128-dimensional vector. So what does it mean? It means we need to generate a Z for the images, because real images, we don't know what Z they were created from, so we need another encoder. So overall, the big BiGAN has a discriminator, it has a generator, and an encoder. And the encoder, well, for the fake data, we simply use the sample Z, so that's fine. And the encoder is then trying to generate a Z which is meaningful from an image. So this is the one where I showed you last time that this is the neural network which learns strong and generalizable representations. And E is trained as part of the discriminator. And this will give you pretty good results, really good generations, even 256 by 256 pixel size generations, which is pretty good. So what changed from 2016 to 2018 is not more data. It was really the compute and architectures. Another architecture and compute change is from this DC GAN to style GAN. So style GAN is the ones where I showed you all these pictures of faces and so on. And of course, you have these fixes with instance norm and a bunch of architectural changes as well. So these were the main points. All right. I've mentioned image-to-image translation. So this is like a conditional GAN. Okay, so conditional GAN is simply where you can input, in addition to a Z, you can also input, for example, a one hot vector, which represents a label or a class, or you can, just like in the VAE part last time, you can input half an image or a quarter of an image and make the output conditional on that. You can also make it conditional on text, for example, and then you can start generating better text, better images that carry a bit more information, for example. And you can keep on going and then condition it on other images, and these could be, for example, sketches, right? So you can make a sketch, and the output could be a whole image. Of course, you need a corresponding data set at that point, because you cannot start without having sketches. But yeah, this allows you to do all these things and also the same stuff that I showed you earlier with the satellite pictures. You can also combine this stuff with the previous lecture as autoencoder. So in the autoencoder, we had that it tries to minimize the reconstruction error. And here we're simply adding an adversarial loss in this latent space Z. And this means that we will now be containing the latent space in a manner that will be easy to sample from. So this Q of Z in this autoencoder paper, that it can be deterministic or it can be Gaussian, just like we had for the VAE, where you use a reparameterization trick. And compared to the VAE was using this Kullback-Leibler divergence to give this P of Z given X structure. And compared to that, the AAE simply uses an adversarial network for this. And you can simply toggle between an autoencoder and an AAE with varying the weight. And in this case, you can see that the adversarial network doesn't need to operate in the image domain. It can simply operate in a latent space domain, right? It doesn't need to be an image model. It can simply be a bunch of MLPs. And of course, as with all of these models, can be extended for conditional modeling. Right. The CycleGAN is another one of those image-to-image models. In this case, it learns a mapping function to go from one domain to another. And the reason why it's called cycle is because you go from one domain to another. So in this case, if you look at, for example, image B, you go from domain X to domain Y, and then you go back to domain X. And if you do that, you should end up at the same place if these mappings were working correctly. And so that's the basic principle behind cycle-consistent learning. So you can get a learning signal, again, just from the data, but you can try to go to a different space and try to come back and this way get a learning signal. All right, finally, this StyleGAN is, again, here I'm comparing StyleGAN 1 with StyleGAN 2. The main differences are here highlighted. These are, as you can see, it's simply tinkering. It's not like something fundamental has changed between these two versions. It's simply having larger models, more compute, and some small changes. Right. What's now, of course, the biggest trend is text-image generative models. And with that, the bottom models. So we had GANs, we had VAEs. We didn't talk about flow-based models. But right now, diffusion-based models are how the best generative models are being made. So we're going to very briefly talk about these. Yep, sorry, yeah.
So for the exam of this course, are we expected to know all these architectures and the big BiGAN and CycleGAN? Are we supposed to know them?
You're not supposed to know the details of these architectures. No, I won't be asking like, what's the third block of StyleGAN? Similarly, I would say for big BiGAN, for example, you would be good to know that the general architecture has an encoder, has discriminator, but not like all the nitty-gritty details, right? So it's kind of like you would be expected to know a transformer. You wouldn't be expected to exactly know how a particular paper that might have been mentioned is implemented or whatever, right? Like I wouldn't ask, for example, about the perceivers architecture in detail, just the general idea. Question?
The slide for the big BiGAN?
Yeah.
Is not on the...
Yeah. So sometimes I do some last-minute changes, and I should have mentioned that at some point. I always re-upload the slides after the lecture, which has the newest stuff in there. All right. Sometimes I also do it just before the lecture, but yeah. All right, so the basic idea of diffusion models is the following, that you actually start at the right, you start with a real image, and you gradually add Gaussian noise. And at some point, T, large capital T, you end up with simply Gaussian noise, which is what you end up with if you just keep on adding noise. And so now this is the process that you're now trying to invert. So all that you're trying to learn is this red arrow that goes from something that's noisy to something that's slightly less noisy. So this is what you're trying to learn. And if you can do that, you can simply apply this all the way from any kind of Gaussian random noise, and you keep on doing that, and you end up at a real image. So it's a completely different paradigm to do generative modeling. So if we can reverse this process, we can generate images by simply starting from random noise. And of course, there's nice mathematics, because diffusion models are one of those actually explicit density models, but still give you really good performances. And you're trying to learn this green function, essentially. The main idea is that these diffusion models basically turn generative modeling into a sequence of supervised models, right? Because you have your image and you apply noise, and so you know exactly how it looked beforehand. So you're simply trying to turn this whole denoising procedure into different steps from t to t minus 1, and you can use that as a supervised learning method. That's a broad idea here, and diffusion models will be tackled more in detail in deep learning 2, actually. So, in fact, the only thing that we're going to talk about this one is that the architecture here is a UNet, because UNet is an architecture which takes an image in and outputs an image. So it's kind of like one of those segmentation architectures. In fact, it was mainly developed for segmentation. And the only difference is that there's an additional time step t as input, because that's what we used for going from very noisy to less noisy. So in addition, the network sort of knows where in this time frame it is. And then what you can end up is the second version of DALI. So this is pretty much what has been used here. So you have your clip objective. So you first train a clip model, basically, which gives you an image encoding and a text encoding. And then afterwards, you use this text encoding to condition a diffusion model to generate something that comes out. And of course, apart from that, there's a 400 million size training data set and the 3 billion parameters that these models have. So these are pretty much how all the improvements got made. Right. Yes?
How do you actually sample from a diffusion model? Because it seems like you give it a bunch of noise and then it turns it into an image, but how would I know that I was going to get a Corby, for example?
Right. So here in this case, you do the conditioning based on the text. So the text will give you a vector, and that's the starting point then. So you're not starting from random noise at that point.
You learn like a conditional distribution.
Yeah, exactly.
Conditional distribution will look like noise, but
yeah, but it is conditioned on this vector, on this blue vector, yes.
But then how do you exactly train it? Because wouldn't you then need to add noise in a way that gets to a text encoded block and not just a random Gaussian noise block?
That's a good point. I think that's the difference between the top branch and the bottom branch you have here. So you have the prior and you have this other conditional part, but I'm also not exactly sure on the details. So yeah, I would have to look that up. But good point. Right. So DALI is, of course, the stuff that we looked at the beginning of the lecture. And there's some interesting stuff happening. So I would encourage you to pay attention in the Fact AI course, because deepfakes are quite a problem, and there's almost this meta-level arms race, of course, between fakers and detectors going on. There's this one video, for example, where Zelensky is seemingly saying, please, all the Ukrainian soldiers, put down your arms, we're giving up or something. And of course, this video actually explains why it's fake and where you can detect it and where did the background come from, where did the foreground come from. I don't think that was even a particularly good deepfake. Nowadays, they're even better, I think. So I'm not sure why they ended up with such a bad one, but the problems are pretty real. So I highlighted some here from this eSafety from the Australian government website. And I really recommend this talk actually on the ethical considerations of generative AI. So this is the last lecture we have today on generative AI. And this video is from 2021, but already back then we had the problems of harassment, abuse, objectification, unethical data sources, cultural appreciation versus appropriation, bias in generative models. By the way, going from left to right is only changing the attractiveness score. So you can tell whoever made that sort of data set, right? And of course, there's even more problems nowadays. So for example, well, this is not really a quiz, but what dimensions need to be considered when thinking about developing the next generative model? Ethics of data set used, bias, representation, consent, copyright of inputs and copyright of outputs, malicious use cases of the trained model, malicious use cases of adapting the trained model or method, 5, effect on surveillance and creative industry, art, and fake news, and of course 6 is the solution, because that's not even all of this. In fact, we often sometimes are encouraged to write about potential impacts in papers as well, in research papers. I've linked a guide on how to think about that. As generative AI is also, and the impacts of it are not limited to just images. So someone ran this generative method which generates new molecules and simply basically turned around the laws. So instead of having, well, almost, like instead of trying to generate molecules which are not harmful, just turn it around and you can generate molecules which are extremely harmful. So in the interview, when asked, he wrote, how easy is it for someone to replicate what you did? What would they need? And they replied, I don't want to sound very sensationalist, but it is fairly easy for someone to replicate what you did. If you were to Google generative models, you can find a number of put together one-liner generative models. And if you were to search for toxicity data sets, there's a large number of open source tox data sets. And you just combine these and you get toxins which are more toxic than VX, which is an extremely toxic chemical. So the topic of generative modeling from all angles is really interesting. And of course, yeah, text is there as well. So I'll leave you with this one summary that the new chatbot from OpenAI left, because there's not much to add. It's a pretty good summary of GANs from the technical side, and also interesting that it doesn't really talk about these issues at all. And with that, thanks, and you'll have, yeah, for those which, by the way, some people had talked about that some of their tutorials are a bit full. I think some people tend to go to the earlier tutorials, so if you prefer less busy rooms, you can simply go to the tutorials which are a bit later in the day. All right, so next week we'll have 2 broadening topics with 3D and physics and molecules. And the basics they will introduce will also be relevant for the exam, but not the details. So again, it's a high-level ideas, and they will be starting with very basics, and then they will be talking about their ongoing research. And it's meant that the basics will be needed to be understood, but not whatever they published a few months ago, basically. All right, thanks. Yeah.
Generative models, is there also like research here going on in that domain? Because I'm kind of interested in looking into that as well, or courses which go deeper.
Right. So. Oh.